Alright, so yesterday we derived Jacobi's equation which had the following form, yeah, and we said that in order to check for the existence of conjugate points you might actually try to do the following, to choose epsilon is a really small number. Okay, so solve this initial value problem with this differential equation and see if, check to see if there exists C in the interval a to b such that Vc is equal to 0. Okay. If not, then conjugate point does not exist. So what do we immediately have if the conjugate point doesn't exist? The moment we have the situation that a conjugate point doesn't exist, we can use this V to construct a suitable W, right? What sort of a W? A W that satisfies another differential equation, a quadratic differential equation, which in turn then enables us to do something else. What exactly? Why are we so keen on this W? Because that's what Legendre did. Yeah, if that W can be found to exist throughout the entire interval, then in a sense we are hoping that we will be able to show that the second variation is going to be definitely the integration of a whole square and therefore positive. So it seems at this point that a reasonable sufficient condition is as follows, that L y prime is greater than 0, there does not exist a conjugate point in AB. Okay, so this is first condition, this is the second condition, and it seems like if we are able to ensure that these two things hold together, then it seems like the solution of the Euler-Lagrange equation gives us an extremal, and with that extremal in place, if you were to check this condition and this holds true, then we have a reasonable degree of confidence in the fact that the extremal we have solved for is indeed a candidate that minimizes your cost function. Yes, but we are not quite done yet, because if you recall, you see, okay, I often tend to sometimes use the star notation, sometimes not, but in general you will understand this, that when we are writing it in this fashion, we are talking about those candidate y's which are extremals, and therefore you might as well put the star. Okay, so now if this is a candidate extremal, satisfies the Euler-Lagrange equation, so what can you say about the first variation? Must vanish due to the Euler-Lagrange equation, that must vanish. So the next term that arises is the second variation multiplied by alpha squared plus these terms, and here is the deal. If we are to have a reasonable degree of confidence that this is indeed the sufficiency condition or the sufficient conditions, we will also have to be able to convince ourselves that this does not dominate this. But in other words, we need to take a closer look at this object here. Yes? You might also alternately say, can we say something more about this fellow? Can we somehow show or convince ourselves that this fellow actually goes to 0 faster, so that we'll always be able to find a small enough alpha staying within which this term gets dominated by this, so that at least the candidate is a local extrema, not just an extremal. So we need to really understand the nature of this object more closely. In order to do that, we shall make use of something that you have learnt earlier in your undergrad calculus courses, which is mean value theorems. Okay. So for the moment, let's keep this as it is here, and let's invest our time and effort towards understanding the mean value theorem, or recalling much of it really. So suppose you have f, yeah, which is say a mapping from R to R, and f is continuous in AB, f is differentiable in the open interval AB, and what else? Fa is equal to Fb. Yeah. So if all of these three hold, then yes, there exists C belonging to the interval AB such that f prime C is equal to 0. This is Rolle's theorem. Yes, you can look up any standard textbook. If you don't remember the proof, you can just look up a standard textbook. It's not really that difficult to see. It just says that if you have a chord that's connecting the function at A and B, the function values at A and B, then you must also have a tangent that's also flat there. Yeah, you can also generalize this, and you can have Lagrange's theorem, if you remember, Lagrange's mean value theorem. Anyway, this will suffice for our purpose. Okay, so let's. So I hope this is, you've recalled this, right? So your memory is jogged. So I'll now erase this and consider f is twice continuously differentiable. Okay, and define phi in this manner. So let's say phi of x is defined as f of x minus f of a minus f prime of a times x minus a minus f beta times f double prime a. Okay. Now you might say, what is beta? Well, beta is what we will decide a while later, depending on how we wish to invoke this condition. So this is to be decided yet, so that it allows me to invoke the mean value theorem in a suitable manner to get to a result that I want. What is the result that I want to get to? We'll come to that very quickly. Now let's look at this. So phi a is equal to what? Sorry, I think there has to be a x minus a whole squared, right? Yeah, I missed that. So phi of a is quite clearly 0. Yes? Yeah. What about phi b? We wouldn't know that unless we knew what beta was. Now if we want phi b to be equal to 0, then we can certainly choose beta in a suitable manner to make sure that that happens. So let's set phi b is equal to 0 and evaluate beta. So what do you think beta comes out to be? F b minus f a minus f prime a times b minus a minus beta times f double prime a times b minus a whole squared is set equal to 0, whereupon what is beta? F b minus f a. Actually we don't need this f double prime a, yeah, I think just that x minus a whole squared will suffice. We don't need that, that's not serving any purpose, right? Just a scaling factor, you might as well get rid of it. Just a constant, right? So if you absorb it here, you call it beta tilde, it doesn't matter. I mean, at least in the differentiation it's just a constant. Yes, so it wouldn't matter. See, the conclusions don't change, no? As long as you have x minus a whole square at x is equal to a, this is anyway 0. Yeah, okay, all right. So then we can get rid of this term everywhere and we can actually evaluate fb minus fa divided by b minus a whole squared plus f prime a divided by b minus a, because one b minus a gets cancelled. Okay, so we have evaluated beta, hopefully that's correct, yeah, right? Okay, now with this being the situation, what do you think is going to be of benefit to me, having ensured that phi a is equal to phi b is equal to 0, and in view of the fact that we've just stated the Rolle's mean value theorem, what is it that we can immediately conclude? There will be a, oh yeah, there will be a negative, yes, thank you, yeah, because the beta gets taken to the other side. Okay, so okay, let's get back to the question then. So what is it that we can now say about phi in view of mean value theorem? There's a reason why we wanted this phi a and phi b to be identically 0, because we want to use the mean value theorem. So what is it going to tell us? That there exists C in the interval between a and b such that phi prime vanishes at C. Yeah, because I am applying, see, whatever is true of f, the same is true of phi, no? Continuous in the closed interval, of course this is also going to be continuous because after all you are just adding some polynomials to it. Differentiable, this is also going to be differentiable. So all those properties are just easy to check, they are going to be true for phi as much as they are true for f. So therefore phi, yes, which one would be sufficient? I'll see, yeah, good question, but we'll actually have to use the double derivative, because the hint is it's a second order condition. Ultimately our variable is not going to be x, it's going to be alpha. This is just something that I'm doing as a, like a math derivation. This x and this ab and that ab are not related, okay. This is just a general result that's true in case of any function, because I'm going to try and derive an auxiliary condition for the double prime. That's why I need the C2. You'll see shortly why we need that. At least you need to be able to differentiate it twice because we use that result. So let's see what this is. So phi prime will vanish at some point C in between this, yeah, okay. So now draw a mental picture. Here is A, here is B, and somewhere within is C. Yeah. What about phi prime A? What can you say about phi prime A? If this is phi x, phi prime x is f prime, yeah, this is 0, this is minus f prime A, so this is f prime A, this is minus f prime A. Do I need to do the calculation, or you can check? So these two will take each other out in phi prime A. What about this? It's got repeated roots, so even after the differentiation one of those survives, so 2 times beta times x minus A, so at x is equal to A, even this vanishes. So the answer is phi prime A is also equal to 0. Okay. What do you think we are trying to do now? Any hints? I've just said this in response to one of your friend's questions, just this few moments back. Sorry? Yeah, because now you see, now you replace this function f that you had with phi prime, because phi is, f is twice continuously differentiable, so phi prime is at least continuously differentiable. It enjoys the same properties as f prime, which is continuous differentiability, so phi prime is continuously differentiable, so phi prime is continuous in the closed interval AB, phi prime is differentiable in the open interval AB, and phi prime A and phi prime C are both equal to 0. So therefore, there exists some C tilde in where? Between A and C, exactly, between A and C, such that phi double prime C tilde is equal to 0. So to complete this picture that we had here, here is where C tilde lies. Now of course if C tilde lies between A and C, obviously a very dangerous term that you should always be suspicious of in general in mathematics when people use it, obviously C tilde belongs to A and B. Here of course you don't have to be so wary because it is indeed obvious. Yeah. So therefore at some point in the interval between A and B, we have the situation that phi double prime C tilde must vanish, but we can actually go ahead and evaluate what phi double prime C tilde is, isn't it? Because we know the explicit definition of phi from this relation here. So what does this give us? Phi double prime x is equal to f double prime x. What happens to the second term? Of course this has already vanished in the first derivative itself, no longer shows up. What about this one? Also vanishes. So this one survives. So what do you have? Minus 2 beta. Yeah, and beta we, as we have evaluated here, minus 2 beta. So implies phi double prime C tilde is equal to f double prime C tilde minus 2 beta. Let's be a little more explicit in our expression for beta here, and what do we have? What do we have? After all, this is 0, right? This is 0. So beta is equal to half f double prime C tilde. Therefore it means that if you multiply both sides by b minus a whole squared, what do you get? F b minus f a is equal to b minus a f prime of a plus half b minus a whole squared f double prime c tilde. Last step, fb is equal to fa plus b minus a f prime a plus half b minus a whole squared f double prime c tilde. What do you think we have just proved or just established through this result? Does this remind you of something? It's eerily similar to the Taylor series, but the Taylor series is after all an infinite series. It doesn't truncate. In fact, if you truncate it at any point, there will be an error. This is an exact expression, save for one difference here. What allows us to get to this exact expression? In Taylor series, you would have replaced the argument of f, f prime, f double prime and everything with a everywhere. Now we are saying that if you truncate it at this point, and instead of using the argument a here, there will always exist some point c tilde between a and b, such that at that intermediate point, if you were to evaluate f double prime, you would actually get an exact expression. Does everyone follow this? So this is an exact expression. Yeah, which means that, of course, b minus a, if you expand in the Taylor series, b and a are very close by. You know that fb is equal to fa plus the first derivative of f at a times b minus a plus the second derivative of f evaluated at a times b minus a whole squared by 2 plus so on and so forth with these factorials and all coming in. But now I am saying you can actually truncate it at the second derivative without any loss of accuracy. This is an exact expression. The only price you have to pay is you have to know which point to substitute in this second derivative. Now, unless you are being very constructive here, at least this expression should make you happy for the reason that you know there exists some such c tilde. Whether or not you are able to exactly tractably compute this c tilde depends on the nature of the function and the nature of the equation that this entails. Yeah. But the fact is that, see, how do you compute this c tilde? You have to go through this mechanism everywhere. Now, I have not said that f is a polynomial. F could be any different kind of function. It's a continuous function, maybe twice continuously differentiable function. That could include all sorts of different functions, right? It's not necessary. It could, that it will give rise to a tractable equation. It can give rise to a transcendental equation even. So in general, it may not be actually possible for you to constructively obtain the c tilde analytically. You might have to use some numerical method. But the point is not that. The point is that I have at least ensured that there exists some such c tilde. And that is all that we need in our proof or in our results. Why? So here it goes. We want to find what this term behaves like, and we want to ensure that this term, so this alpha squared, predominates this. This is an approximate expression. If you truncate it at this point, then you will be making an error of the order of alpha squared like this. But now, in view of this result, I might as well write this in the following manner, where this is j y star plus alpha squared delta 2 j y star g. What else? What else do you think? What do you think you need here? Yeah, so what do you want to do here? See, this will have to be evaluated at some intermediate point between 0 and alpha, because now alpha is your variable. So once you have fixed up alpha, you cannot evaluate it at exactly at alpha now. You have to choose a point, say gamma, in between that. yeah, and that is exactly going to lead to the error between the exact expression if you were to truncate it at a suitable point, suitable intermediate point. So you have, for example, say this line here, suppose this is 0 and this is alpha. So in general you are going to be evaluating all of this at y star plus alpha g, but instead if you choose some intermediate point here, say gamma here, by this particular result that we have here, you can safely truncate it without carrying this burden of this higher order terms. Look at this as a function of alpha, that is what we do, right? Every time we were faced with this optimization problem, whether in finite dimensions with in the Euclidean space, what did we always do? We essentially always transferred it to a function of a single variable such as alpha. That is exactly what we are doing here as well. Let's be a little more explicit then. Let's just write down that expression and see what it looks like. You already know what this delta 2 j g evaluated at y star. What did this look like? Integration in terms of the Lagrangian, I mean. Just recall, this was a to b, what was it? L y prime times g prime squared, writing the shorthand one, yeah, g prime squared, and let's cut to the chase and get it in the form that we represented it through p and q, yeah. So we have to absorb the half here as well, I suppose, right? If you want to do that, you have to absorb the half within, because this was our p, remember? What was q? What was q? Lyy minus ddx of Lyy prime, wasn't it? Yeah. Again we had the half, I believe, right? So Lyy minus ddx of Lyy prime times g squared, correct, into dx, right? Now in addition to this you had the higher order terms. If now instead you were to evaluate this at an intermediate point, okay, so at this intermediate point, say gamma between 0 and alpha, such that now you need not carry forward the higher order terms. Are you with me on this? We have j evaluated at y star plus alpha g. Look at it as a function of alpha, that is equal to j y star independent of alpha plus the first variation vanishes because it is an extremal. So because of Euler-Lagrange equation, the first term after j y star is the second variation, which is alpha squared, then the second variation, right? Now the second variation, if you evaluate it at alpha itself, by which I mean that all these terms get evaluated at alpha, these things here, then you will have to also carry those higher order terms like O alpha squared, order of alpha squared. Instead, if you were to evaluate the pass on the arguments of these fellows at x, y plus gamma g, y prime plus gamma g, but gamma is some number sitting between 0 and alpha, which allows you to, which takes the place of the c tilde here essentially. Then you will get an exact expression. And again I repeat, I am not interested in actually explicitly evaluating what gamma is. I am just happy with the fact that there exists some such gamma, which is exactly what I have proved here. Do you see the analogy here? Maybe the notation was bad, maybe that a and b over there you are just relating to the a and b here. Please don't. The variable over there was x, the variable over here is alpha. Yes? So an intermediate point, at an intermediate point within that interval, if you were to evaluate the second term in the Taylor series expansion, You could have just truncated it there without any error. That's what this mean value theorem's application tells us. So let's define, with that in mind, let's define tilde terms like so. Evaluated at x, y plus gamma g, y prime plus gamma g prime, and L y tilde as what? L y evaluated at x, y plus gamma g, y prime plus gamma g prime. What is this gamma? I repeat, at the cost of boring some of you. What is this gamma? This gamma is a specially chosen gamma which will allow me to truncate at the second derivative point itself, and I don't need to go beyond that. It will give me an exact expression. Okay? And by the same token, you can have y prime, define that L y prime evaluated at x, y plus gamma g, y prime plus gamma g. So what is the advantage of all this? On the one hand, you have the approximate expression. On the other hand, you have the exact expression. If you take the difference between the exact expression and the approximate expression will contain the term O alpha squared. Yeah? So here's how it goes. You have j y star plus, let's look at the exact expression here. Yeah? On the one hand, this is true of j evaluated at y star plus alpha g, but this is also equal to j y star plus alpha squared by 2 integration a to b L tilde y prime g prime squared plus 2 L tilde y prime g prime plus L y g squared dx, and that's it, no extra term. This is the exact expression. So these two are equal. Yeah, one is an exact expression based on the mean value theorem we've just proven. The other is kind of like the Taylor series expansion with respect to alpha. Now if you equate both of these, you can of course immediately chop off the common terms, and it leads to the following characterization of this term. What is it? It's actually quite simple. A to b L tilde y prime minus L plus 2, okay, there's gonna be a alpha squared by 2, right? Yeah, 2 L y prime tilde minus L y prime plus L y tilde minus L y g squared. This whole thing gets integrated. That's your error. Okay.